Hello and welcome to the second episode of our series of graph analytics and algorithms. In this episode, we will discuss how to improve graph algorithm efficiency. As we know, algorithm can be viewed as a step-by-step procedure for solving a problem. First of all, it must produce the accurate or expected results. Second, we require the algorithm not to crash under any circumstances, which we call robustness. When both are satisfied, what makes an algorithm great depends on how fast or efficient it is, especially when it's applied to real businesses. The improvement of algorithm efficiency can contribute to impressive gain of profits, which is often measured by TCO or ROI. So we wonder, what makes an algorithm efficient? What factors should we consider? A common way to talk about algorithm performance is time complexity. It's estimated by counting the number of elementary steps performed by the algorithm to finish execution. It's denoted by the big O notation, such as O1, O log n, On, or On square, where n represents the size of the dataset. Time complexity does not really mean the execution time of an algorithm, but only shows how the execution time grows when the dataset gets bigger. It can be reduced by improving the implementations of the algorithm, such as replacing some time-consuming operations with some lighter steps, which lead to the same results or reasonable estimations. The other three factors we will discuss further today are data structure, software engineering, and architecture design. We will see how they would affect the algorithm efficiency. Start with data structure. Algorithms must be run on some data structure. Traditionally, there are two main data structures to represent graph that are adjacency matrix and adjacency list. Let's use the graph here to illustrate. It has 6 nodes and the edges are directed. Adjacency matrix uses a matrix of 6 by 6. Each element in the matrix is the index of edge pointing from node of the row to the node of the column. The element is empty if there is no edge. The drawback of matrix is obvious. The matrix is very sparse with the occupation rate less than 20%. More than 4/5 of the storage space is wasted. This kind of waste is not affordable in real-world scenarios. Adjacency lists represent graph as an array of linked lists. Each node forms a linked list with all its adjacent nodes and edges. Adjacency list is relatively widely used, although it has some pain points in terms of accessibility. Because random access is not allowed in linked list, elements can only be accessed sequentially. So as the number of nodes and edges grows, the complexity for reads increases accordingly until becoming impractically expensive. We are not saying that matrix and linked lists are bad. Each data structure has pros and cons. They could be perfect under some circumstances, but for graph computing, we should expect something that works more productively. So speaking of designing a data structure for graph, I want to introduce a pair of concepts, that is native graph versus non-native graph. We have a small table here to show you the difference. About the source, the storage and processing scheme of native graph is specifically designed around graph from scratch. Accordingly, it's called non-native graph if it's built on some existing relational or NoSQL databases. As for optimization, native graph is optimized to better reveal the correlation between data, which lays the foundation of performant graph traversal. At the meantime, graph traversal is not the #1 consideration for non-native graph architecture and data structure. So clearly, native graph should do the work. And every native graph vendor has its well-designed data structure for graph. What Autopar has utilized is vector of vectors in C++. We have the same graph as we saw at the previous slide. In vector of vectors, each node stores a vector which contains all its neighbor nodes and the corresponding edges in both directions. If it's outbound edge, it's stored as 1 and -1 for inbound edge. This design of data structure assures O1, a constant time complexity to locate any node. For edge, it's O2 if you locate it by its start node and end node. With this kind of data structure and some sophisticated software engineering, highly efficient and deep graph traversal becomes reality, and graph algorithms can be executed in a lightning-fast fashion. Next influencing factor is software engineering. Given an algorithm, it can be implemented in different programming languages. For sure, the execution time varies greatly from one language to another. Which programming language is the best? We all know there is no simple answer, and it's restrained by factors such as development environment, succinctness of code snippet, etc. We have a table to present. It comes from a paper published by some MIT computer scientists. The authors want to illustrate the potential gains from the improved software engineering. So they considered a simple problem of multiplying two big matrices. The experiment starts with Python. This popular high-level programming language takes around 7 hours to compute. In version 2, coding in Java produces a speedup of 10.8 times. In version 3, coding in C produces an additional speedup, yielding an execution time that is 47 times faster than the original Python. Java and C are more static and compiled language. They avoid the extraneous work that Python does under the hood to make the programming easier. And coding in C is more onerous than coding in Python, and Java lies somewhere in between. The improvement doesn't stop there. Opportunities also exist in tailoring the code to exploit features of the hardware. Version 4 leverages parallelism, and version 5 leverages locality of memory. And eventually, by exploiting both parallelism and locality plus Intel's AVX instructions, it's over 32,000 times speed up compared to the original Python. Indeed, this tailoring process requires the programmer to be equipped with good knowledge and skills, and the payback is great productivity. Other than data structure and software engineering, system architecture optimizations are also crucial in elevating system performance and algorithm efficiency. We will illustrate 4 key points to make a graph system fly. First, storage in close proximity to compute. By looking at the 7-layer stack from networked storage to SSD to CPU, you should realize that the data processing power difference is exponential. By saying exponential, we are talking about latency from months all the way to genuinely real time, which is in the range of 100 milliseconds to even a couple of 100 microseconds. Parallel computing shouldn't be stranger to server-side developers and users. However, pushing the limit to make things run with high-density parallel graph computing can truly accelerate most algorithm and query execution by 10-folds or more. Data persistency and distributed consensus are the two key considerations when building an industrial-grade graph database. They both ensure asset can be achieved across multiple instances within one database deployment. We will conclude this video by quoting the Executive Office of the President of the United States. They said, in many areas, performance gains due to the improvements in algorithms have vastly exceeded even the dramatic performance gains due to the increased processor speed. Thank you for watching, and I'll see you next time.